Okay, so today we're starting our discussion of chemical quantities and stoichiometry, and key in that is a discussion of moles and molar mass, and so what in the heck are those things? Okay, so our essential questions remain. What are chemical reactions and how do they occur? And then how do we keep track of atoms during chemical reactions? And then more practically for a chemist, right, working in the laboratory, how do we keep track of the material we're using? How do we know how much like physical material we're going to start with and then how much physical material we're going to end with when we perform a chemical reaction, right? Or when we try to study some chemical process or reaction, right? Like what's going on and how are we going to keep track of everything? So I'll go ahead and show you something that you're familiar with, right? And I'll ask you a question too. So here's a reaction. You've seen this reaction before. So CH4 plus O2 yields CO2 plus H2. Oh, that's a bummer. Okay, let me erase some of this. It's going to be the same equation. I'm just going to move it to the left so we can actually get all of it on the screen. Getting reaccustomed to the space constraints that I have. So CH4 plus O2 yields CO2 plus H2O. Okay, so this is a reaction we're like used to seeing, right? We've seen this before. Can anybody help us balance this chemical equation? Right now it's not balanced. Can anybody help us balance it? Nobody knows how to balance this guy?
Do you put a 2 in front of on the right side?
Which one, the CO2 or the H2O?
For the H2O.
Don't you put it in front of the CO2?
Good. So we've got we could, right? But here's the issue. We'd have 2 carbons, and then that would be unbalanced because we've got 1 carbon on the left. So right now the carbons are balanced as written. We've got 1 on the right and 1 on the left, and we want to go ahead and just leave those as they are. Does that sound good? So the carbons are balanced, right? But why did Therese do this? Okay, she said to herself, how many hydrogens do we have on the left side here?
4.
Right. And then we had 2 to start with, but if you multiply 2 times 2, how many do you get on the right?
4.
4. So now we've got 4 hydrogens on the right to match our 4 hydrogens on the left. And so we're happy. Okay, the hydrogens are happy. Those guys are balanced. All the atoms want to be balanced. Okay. So now we've got balanced hydrogens, but something else looks wrong, right? And it has to do with the oxygens. We've got 2 on the left, but we've got 2 plus 2 times 1, that's 4 on the right. So we've got 2 oxygens on the left, 4 oxygens on the right. What do we do to balance this situation?
You put a 2 in front of on the left side.
In front of the O2. Very good, Therese. And so then we've got a balanced chemical equation, okay? On the left side, we have 1 carbon. On the right side, we have 1 carbon. On the left side, we have 4 hydrogens. On the right side, 4 hydrogens. On the left side, 4 oxygens. On the right side, 4 oxygens, okay? So that's a balanced chemical equation. All right, so we've kept track of all of the atoms, right? Okay, so can anybody remind us what kind of reaction this is? What is this?
So combustion?
Yeah, right. We're combining with which element here tells us that we've got a combustion reaction going on. What's our giveaway?
Oxygen.
Oxygen, right? When you combine with oxygen, you have a combustion reaction. Good. So we're combining over here with this oxygen, and we're saying to ourselves, oh, okay, something combining with oxygen, that's probably a combustion reaction. And indeed, this generally is. So this CH4 is methane. That's the natural gas that comes out of your stove. Okay, so methane, and that's natural gas. And if you look at the back of a bus, on the back of the bus, you'll see this little diamond, and it's going to say C for the buses that operate in San Diego, that stands for compressed natural gas. Okay, so those buses actually run on this chemical reaction, this methane combustion. Pretty cool, huh? Okay, so what's next? So here's a question, right? If I start with, let's say I start with 10 grams of this, right? How many grams of this do I need for a complete chemical reaction? And then how much of this do I get? And how much of this do I get? Okay, so like, for instance, I know that if I start with 1 molecule of CH4, I need how many molecules of O2? Guys, what do we see there? How many molecules of O2 are written in that balanced
4.
chemical equation? 4 oxygen atoms, but how many molecules of O2? How many O2s?
2.
2, right? You've got 2 oxygen molecules there. Okay, so 2 oxygen molecules plus 1 methane molecule. Okay, so who wants to take a stab then at how many grams of oxygen I'm going to need? Like if I have 1 methane molecule, right, to 2 oxygen molecules, right? How many grams of oxygen am I going to need? If I've got 10 grams of methane, how many grams of oxygen am I going to require? Anybody want to take a stab? Nobody. Okay. So in that case, we'll go ahead and leave it a mystery. Okay. I won't pose any false answers or so forth. We're just going to leave it a mystery. But I'll tell you that it's not straightforward. Okay. There's some calculation that has to be involved in figuring this out. So in order for us to do that, we need to understand something called the mole. Okay. And then we'll get back to what we're dealing with in terms of this reaction, in terms of methane combustion in a minute. All right, so if everybody's got the board written down, I'm gonna go ahead and erase. Take 3 seconds though to take a screenshot if you don't have everything copied down. But this is the big mystery right here, like how many grams of this do we need, and then how many grams of this guy and this guy do we get, right? That's our big mystery that we're gonna be thinking about over the course of this week, okay? Maybe just over the course of today, depending on how smoothly things go today. So, all right, so we really want to know what's going on here. So I'm going to go ahead and erase the board in 3, 2, 1. Okay, and in order to understand what we're dealing with here, we have to understand something called the mole. Okay, the mole. Okay, and I'll go ahead and capitalize mole. The mole. Okay. So what's the mole, right? What is the mole? So a mole.
Look, it says right here. Oh, not banned. They get rejoined. Banned.
So
I don't want them near. I don't want them
guys,
near.
please mute. If there's talking in the background, please mute. So a mole. A mole. Actually, let's go with the mole. So the mole, right? It's just a number, okay? So the mole is just a number. So the mole stands for 6.02 times 10 to the 23rd. Okay, that's the mole. It's literally just a number, but it has this special significance in chemistry that we're going to talk about. So 6.02 times 10 to the 23rd, and I'll write a better 3. Okay, 6.02 times 10 to the 23rd. That's maybe a better 3. So just like a dozen. So like here's our little note, right? Just like a dozen means 12. That needs to be a comma, but like a better looking comma. Okay. A mole means 6.02 times 10 to the 23rd. Okay. So just like a dozen means 12, a mole means 6.02 times 10 to the 23rd. And that's just what you need to know. Okay. So like if you've got a dozen of something, how many of that thing do you have?
12.
12, right? If you've got a mole of something, how many of that thing do you have? I want everybody to say it. Okay, how many of that thing do you have? You have
6.2 times 10 to the 23rd.
yeah, 6.02 times 10 to the 23rd copies of that thing, right? And so why do we care, right? Why does a chemist care? What's the significance, right? So here's a really cool thing that allows us to use the mole in chemistry, okay? So every Alejandro, mute yourself. Every chemical, every element on the periodic table, like take carbon for instance, right? So carbon is atomic number 6, but it has a mass number of 12, right? So that mass number 12, that mass number indicates, and I'm going to use a double-tailed arrow, that each carbon atom has an average atomic mass of 12 AMU, where AMU stands for atomic mass unit. Okay, you might write that down. AMU stands for atomic mass unit. And so this is the really interesting thing. I'm going to erase what's written on top here about the mole. Just going to erase this little bit. Hope everybody's got that in his or her notes. If not, this video will get uploaded, and so you'll be able to access it. So here's the really cool thing, right? That takes us from AMUs to something we can measure physically, right? So like, do you have a scale at home that you can use to measure your mass in atomic mass units? No, right? Like this is probably the first time you're hearing of this unit, unless you remember me saying it or mentioning it earlier in the class, right? Atomic mass units. We don't measure things in atomic mass units. We just don't, right? We measure things in pounds or grams or kilograms, etc. We don't measure tons. We don't measure in atomic mass units. And so all of our atoms, right, are given masses in AMUs, but we as chemists have to be able to get from the atomic world back to the physical world, right? So how do we do that? We do that using the mole, okay, when we're thinking about chemical quantities and physical amounts of chemicals. So it turns out that 1 mole of atomic mass units equals 1.0 grams, okay? That is 6.02 times 10 to the 23rd AMU equals 1.00, write a better 0.00 mole, okay? 1.00 mole. And that's not a mistake on my part, okay? And that's not a misspelling. The abbreviation for mole, M-O-L-E, is actually M-O-L. So chemists love to abbreviate whenever they can, and they abbreviate mole, M-O-L, to avoid having to write an extra E, okay? So that's the abbreviation for mole. And so because of that, you can say that so each each carbon atom has an average atomic mass of 12 AMU, right? And then I can actually turn that little period into a semicolon, and I can say, we use a semicolon to connect two independent clauses, okay? Language constructs that could, or phrases that could stand as sentences if we wanted them to. So the mass number of each carbon atom has an average atomic mass of 12 atomic mass units. And so 1 mole of, what the heck? What in the heck? Something weird happened on my screen such that I'm like zoomed in, and I don't know how that happened. And so like I'm trying to figure out what in the world happened over here. Okay, that's weird. Okay, I'm good though. 1 mole of carbon has a mass of 12 grams. Okay, 1 mole of carbon has a mass of 12 grams. So if you have 6.02 times 10 to the 23rd carbon atoms, those carbon atoms will have a total mass of 12 grams. Okay, so I'm gonna let everybody get that written down. I'm gonna ask you if you have any questions about what I've had to say, because this is a lot, okay? So I've just given you a lot of information, and it's quite profound, actually. We're gonna spend a while just getting comfortable with these concepts and definitions and their immediate applications. So what are some questions that we have immediately, right now, like off the top of our heads?
What significance does like the 12 have? Like I'm confused on like the how to calculate it.
You don't calculate this 12. This 12 over here,
Yeah.
that's given to you from the periodic table.
Well, I know, but you're saying how like each has an average atomic mass of 12, and then how do you calculate it from there? Like, do you just times it by 6.02 times 10 to the 23rd?
So like, how do you, like, where does the 12 come from?
Yeah, I'm kind of confused on like how to solve like the mole, or is just the mole like that number specifically, the equation?
Okay, the mole is this number,
Mm-hmm.
6.02 times 10 to the 23rd. And when you have that many atomic mass units, you get, oh, I wrote 1 mole there. Oh no, sorry, yeah, equals 1 gram. AMU equals, I'm sorry, I wrote 1 mole over here. That's confusing, guys, I'm so sorry. 6.02 times 10 to the 23rd, AMU equals 1.00 grams, okay? 1.00 grams. It does equal 1 mole, but it's 1.00 grams, okay? So that's something that I left out. So 1 mole of atomic mass units equals 10 grams. And so 1 mole of atomic mass units equals 10 grams, right? And okay. And 6.02 times 10 to the 23rd AMUs equal 1 gram, okay? 1 gram.
Okay.
All right. So that's that piece. But regarding the periodic table entry here, when you look at the periodic table, you're going to see two numbers for every single atom. You're going to see the atomic number, and you're going to see the mass number. Okay, the atomic number and the mass number. That's what you're going to see. So if you see the atomic number, what does that give you? Do you know, Paula? Did you guys learn this in your I don't know where you were going to school before this, but did you guys learn that in chemistry, or have you been in chemistry this or not yet?
Yeah, I have. Yeah, I have.
Okay.
Does it give you the protons?
Yeah, good. The number of protons, right? And the mass number is what?
The electrons, I think?
No. Who can
Oh,
tell Paolo what the mass number is? Waiting for somebody to help out. We all know this. Remember, we drew our little circles and like you had 6 little pluses, right?
Oh, it's the number of protons and neutrons, right? Like
Paolo, was
combined?
that you?
Yeah, that was me.
Good, yes. It's the number of protons plus the number of neutrons, okay? The number of protons plus the number of neutrons. And so that's just given to us in the periodic table. That has to be determined experimentally. We don't calculate that, okay?
Mm-hmm.
So once you look at your periodic table for whatever atom you've got, right, or whatever element, you say to yourself, okay, sure, this is the mass number. And the mass number tells me that and I don't like the way I wrote this. I said each carbon atom. I'm going to say carbon atoms have instead of each carbon atom has. So carbon atoms have. That's just a better way to write that. Carbon atoms have an average atomic mass of 12 AMU. So 1 mole of carbon has a mass of 12 grams. Okay? Does that make sense now, or do you still have a question? Because I want to know if you still got a question.
No, I'm good.
You're
I
good.
think
Okay.
that's better,
All right.
yeah.
Any other questions? Okay. Well, I hope that exchange cleared up any confusion that anybody else might have had. So, okay. So if you look at the periodic table, and now I need to pull up a periodic table on the third screen. So please go ahead and pull up a periodic table. A really good website is ptable.com. So if you just type ptable, it'll pull up a really nice periodic table. And so what we're going to think about is calculating molar mass. Okay? Welcome, Angeles. Good to see you. So calculating molar mass. Okay. Calculating molar mass. All right. So let's say we're dealing with a compound that's pretty, like, let's take a look at like this one, right? So one compound that's pretty interesting is O2. Okay? And you ask yourself, okay, what's the molar mass of oxygen, right? Molar mass is what? So what's the molar mass of oxygen, right? So O2 has how many oxygen atoms in it? It's 1 molecule of oxygen. So the Lewis structure for O2 looks like this. Welcome back, Anthony. The Lewis structure looks like this. Okay. Anthony, are you there? Can you hear me? This is tough. Okay, Anthony, please chime in, okay? I'd love to hear from you so I can actually like confirm that you're here. All right, so this is oxygen, right? 1 molecule of oxygen has 2 oxygen atoms in it, okay? So this is the formula, and this is the Lewis structure for oxygen. Somebody just chatted with me. Okay, no worries, Angeles. Thank you for letting me know. All right, so this is an oxygen molecule, and we can represent it as a chemical formula or as a Lewis structure. Okay, so we've got those 2 representations, right? And we've got to ask ourselves, what's the molar mass of molecular oxygen? And so molecular oxygen is made up of oxygen atoms, and oxygen atoms have an atomic number of 8 and a mass number of 16. Okay, if you look at the periodic table, you'll just see that right away. And so my question is, what's the molar mass of oxygen?
$16.
So what's the molar mass of O2? Okay, so I'm going to write a little question mark there, right? And then I'm going to redraw my little periodic table entry around this guy. What's the molar mass of O2? Okay, so how do we find that? So Paulus says 16, right? But remember, that 16 is for atomic oxygen, not molecular oxygen, okay? Atomic oxygen just has 1 atom of oxygen. Molecular oxygen has how many atoms of oxygen? Eduardo, are you there?
Yeah.
Okay, so Eduardo, how many oxygen atoms are in this molecule of oxygen? How many do you see?
Wait, which one?
Right here, I just circled this guy. Here or here, how many oxygen atoms are in a molecule of oxygen?
There's 4 on the left and the right.
No, so like I see what you're saying, but like I'm just representing them two different ways. So this picture represents what this chemical formula um, is showing us. Okay, so like this picture represents this chemical formula. Okay, so look at one of them only. Like let's say look at this one. How many oxygen atoms are here?
2.
Good. Okay, and each oxygen atom has a molar mass of how many grams per mole?
16. My bad.
16. Okay, good.
I was about to say.
So
Yeah.
right. So we've got two of them, and they have a molar mass of 16. So then what's the mass of the two of them combined? We've got a molar mass of 16 grams per mole, right? Okay. Okay. And we're going to multiply that whole thing times 2. What's that give us, Eduardo?
$32.
There we go. Equals 32 grams per mole. Okay. And that's the mass of oxygen gas, okay, per mole. So the molar mass of oxygen gas is 32
That's
grams per mole. All right. So if you've got 1 mole of oxygen, you've got 32 grams. Okay. Any questions about that? All right. So let's do another calculation. And I'm going to erase, or should I have left that up on the board for a little longer? Are we still copying? Okay. So take like a minute or so to copy this down. Who's got a question for me? Nobody has a question? Okay. I want to hear from Alejandro. Alejandro, how's it going? Are you understanding this or do you have a question?
No, I'm just looking over them.
Okay. Jasmine, how are you doing?
What?
How are you doing? Does this make sense to you?
Oh yeah, yeah.
Okay. Jalen, what about you? How are you doing? Does this make sense? Jalen, I can't hear you.
Yeah, it does.
Does this make
Oh.
sense?
Yeah.
Yeah? Okay. So Jalen, help me out with the next one. At least help get me started. And then Valeria, I'm going to want you to help out too. Valeria, are you there? Valeria, I can't hear you. Are you there?
Yeah, I'm here.
Okay. All right. So oxygen, right? Oxygen had a molar mass, or sorry, oxygen, yeah, oxygen gas had a molar mass of 32 grams per mole. Okay, we calculated that, right? Let's calculate the molar mass for water. Okay, so water is H2O, right? And we can draw the Lewis structure of water like this. Okay, so I'll make this a little more explicit with what I'm doing. So I'll put formula. And that's the molecular formula, okay? And then this is the Lewis structure. Okay, and then chemical form, there's a molecular formula. Molecular formula. and then the Lewis structure. Okay, and so the molecular formula is H2O, right? And the Lewis structure is HOH. Okay, and so we have two different atoms here, right? We have O, which again has atomic number 8 and mass number 16. But we've also got H, which has atomic number 1 and mass number 1. I'll just put a 1.00 there, okay? Atomic number 1, mass number 1. So what's the molar mass going to be? Right, like how do we find this molar mass? So, okay, so Jalen, take a look at this molecule, right? How many hydrogens do we have and how many oxygens do we have?
We have 1 oxygen, 2 hydrogens.
Good, okay. So then 2 hydrogens and 1 oxygen. Okay, and Valeria, what's the molar mass of an oxygen atom?
What did you say?
What's the molar mass of an oxygen atom?
I don't know.
Okay, have you been paying attention or have you been tuned out?
No, if you pay attention, I'm taking notes.
32.
Notes. Okay. So what was the molar mass of carbon, Valeria? What's written in your notes? Alan, that's close, but sorry. Oh yeah, I see, Alan. You're finding the final answer over here. Yes, that's correct. Good job, Valeria. What was the molar mass of a mole of carbons, or the molar mass of carbon? What do you have in your notes? Are you there?
What was it? Was it 32?
No, that's oxygen gas. What's the molar mass of carbon? Look a little earlier in your notes, from earlier in the class period. What's the molar mass of carbon?
Twelve.
12, good. Where was that number written, right? Where was that number written in the periodic table entry for carbon? Was it the top number 12 or was it the bottom number 12, Valeria? Valeria, I can't hear you.
Oh, what did you say?
So where was that number 12 written, right? For oxygen, was it the top number in the periodic table entry? Sorry, for carbon, was it the top number in the periodic table entry or was it the bottom number in the periodic table entry? When you look at your periodic table entry for carbon, where was that number written?
The bottom.
The bottom, good. Okay, so the bottom number tells us how many grams per mole. So when I ask you about oxygen, how many grams per mole do we have if we're looking at the bottom number? Huh? Everybody except for Valeria should be muted. Valeria, how many grams per mole for an oxygen atom?
16.
16, good, okay. And then Jalen, how many grams per mole for a hydrogen atom?
1.
1, very good. And how many hydrogen atoms do we have, Valeria, in our structure?
2.
2, okay. So to calculate the molar mass, guys, what we do is we say 16, the molar mass of 1 oxygen atom, right? Plus 2 times 1, which is the molar mass of the hydrogen atoms. That's going to give us 18, and our unit is grams per mole. Okay? 18 grams per mole for water. Okay, any questions about that? Okay, so now we're going to go ahead and look at 2 more chemicals. 2 more chemicals. So go ahead and copy this into your notes. And I'm going to erase the board for the most part. All right. So we've got CO2, and the Lewis structure for CO2 looks like this. Okay. And we already said that oxygen has a molar mass of 16 grams per mole. And earlier we said that carbon has a molar mass of of how much? Alana, how much is our molar mass of carbon? Alana, are you there? I can't hear you.
Hello, can you hear me?
Yeah, Alana, what's our molar mass of carbon?
Isn't it 16G
No,
over
that's
F?
oxygen. Oxygen is 16 grams per mole. I'm talking about carbon over here. What's the molar mass of carbon?
Oh, wouldn't it be 12?
12 grams per mole. Good. Okay. Now, let's look at the molecule here, right? So Alana, how many carbons do we have in this
One.
molecule? One, right? So to calculate the molar mass of the molecule, you put 1 times carbon's mass, which is 12, okay, plus, Jamie Lee, how many oxygens do we have in that molecule? Jamie Lee, are you there? Jamie Lee, I can't hear you.
I forgot I was muted. 12.
Okay. So, okay, right. 12 is the number of grams per mole for a carbon atom, but how many oxygens do we have in this molecule? I've circled the molecule. How many oxygen atoms do you see? How many O's?
2.
2, okay. And then what's the molar mass of oxygen? It's circled in the oxygen periodic table entry. What's the molar mass of oxygen?
16.
Right. So to calculate the molar mass of CO2, we do 12 plus 2 times 16, okay? And that's going to give us 44. And our unit again is grams per mole. Okay? 44 grams per mole. That's for CO2. Okay. Any questions about that bad boy? All right. So we're almost done. We're actually almost done. I'm going to erase, and I'll go ahead and finish up our last example in the interest of time. So the last chemical that was in our chemical equation that we started with today was CH4. So we were looking at methane combustion. And CH4 has the Lewis structure C, H, and then we'll go H, and then we'll go H, H like that. Okay, and what's the molar mass of CH4? That's what we want to know, right? So there's carbon, and there are 4 hydrogens. Okay, hydrogens 1 and 1. Okay, so you've got carbon, which is 12, plus 4 hydrogens, 4 times 1, is going to equal 16 grams per mole. Okay, so that's what we have, 16 grams per mole methane. All right, so our question at the beginning of the day was what happens when methane combusts in terms of physical quantities, right? Masses of chemicals involved. So I'll go ahead and put that, I'll put this guy back on the board for a second just so you guys can see it. And then I'll pause in case does anybody have any questions about methane combustion, or sorry, not methane combustion, about the molar mass of methane, okay? Which we just calculated here. Does anybody have any questions about the molar mass of methane? Okay, now I'm gonna erase the board in 3 seconds. Okay, so take a screenshot if you need to preserve it for a little bit longer, but I'm gonna erase in 3, 2, 1. Okay, so there it goes. So our question at the beginning of the day, our big question was, what happens when methane combusts, right? So you've got CH4 plus 2 oxygens yields CO2 plus 2 water molecules. Okay, so what happens when this happens at a much larger scale, right? So let's say we're dealing with molar quantities of each molecule shown. Okay, so if you've got 1 mole of methane gas, you've got, as we said earlier just now, 16 grams. If you've got 2 moles of oxygen gas, you've actually got 2 times 32, which equals 64. So you've actually got 64 grams of oxygen gas. If you got CO2, we just said a little bit ago that you have 44 grams. And if you've got 2 water molecules, you've got 2 times what we calculated, which was 18, right? That equals 18 grams per mole. That equals 36 grams. Okay, and so that's how many grams of everything we have when we actually do this reaction at what are called perfect stoichiometric ratios. So when this reaction happens, ideally, 16 grams of this react with 24 grams of oxygen, which produce 44 grams of carbon dioxide and 36 grams of water, okay? That's what happens when 1 mole of methane combusts. And so here's something that's really interesting. If you add these 2 up, I'll do a little bit better. If you add these 2 guys up, you get 16 plus 64, and 16 plus 64 is going to be 80. And if you add 44 and 36, you get 80 grams, okay? And that leaves us with a really cool little tie-in to a really important law of thermodynamics, which is the law of conservation of mass. Okay, so we can tie this to chemical reactions by saying that mass is neither created nor destroyed during chemical and then reactions. Okay. So now, when you see those buses driving around, or when you turn on the gas stove at your home, or when your gas-powered water heater or fireplace is warming up the water or the air in your home, you'll understand exactly what's going on at a chemical level. All right, I have time for maybe 1 or 2 questions about this last page.
I have a question, Dr. J.
Go for it.
Can you like move the board up because I can't see the bottom, like the bottom part?
I can't really move the board, no.
Oh.
You might be able to move your dock or something, or minimize your window and scroll or something, but I can't really move the board. Any other questions?
I have a question.
Yeah.
For the you know how we calculate each molar mass?
Uh-huh.
Do we have to separate them and then add them on each equation, like on each side of there?
That just proves to you that there's no loss of mass theoretically in this system.
Okay.
Okay, so when this reaction happens, theoretically we don't observe any loss of mass, and we also don't observe that in practice. Okay?
Okay.
Okay. All right, any other questions? All right.